everyone, and welcome to the new discussion which we are going to have on Theis equation, assumptions and application. This is part 2. Earlier we have discussed assumptions and some of the applications of Theis equation. So, let us start with this the Cooper and Jacob, after the development of this Theis equation in 1946, they developed further or modified the equations by Theis for small values of r, that is the radius or distance you can say, and the large values of t, that is the time, and where u is small, and therefore, the series terms in the equation which is given below becomes negligible after the first two terms. So, this second equation as written here, earlier we have also discussed this, that u equal to r square s upon 4 capital T and T. So, this because of this the drawdown can be expressed by asymptote, that is the middle value, and we can write as s is equal to q upon 4 pi t bracket minus 0.5772 minus log r square s by divided by 4 capital T and T. So, in this way we can also modify the equation. Now, the Cooper and Jacob method, they have rewritten changing the decimal logarithmic reduced to s equal to 2.30 q upon 4 pi t log 2.25 capital T T divided by r square s, and this becomes our equation number 5 in this case. And therefore, a plot of drawdown which will have s storativity in here it is given here storativity versus time can be given, and this would be a straight line. So, whichever the value we get we can fit over this, and this is the fit line, the best fit line you say, and these are the pumping test data which are coming, and they should turn up in a straight line when we plot this xy plot between s and t. So, you recall that what we said, that small values of r and large values of t, which we will see how. So, now whenever we want to determine the with the time longer time what would be the value and other things, then this graph can be used to determine those values, because it is a straight line. Here the t0 is given here, which is 0.39 minutes, and of course, the t can go for very long time also. That was the purpose of the method given by Cooper and Jacob. Now, we can project this line in which s would be the 0 and where t becomes equal to t0 in this figure, which is given here on the right side, and therefore, we can write that the 0 equal to 2.3 q and divided by 4 pi t, t is capital here, log 2.5 t t0 upon r square s, and this will allow us to for the above to hold true, that is log 1 equal to 0. So, we can write like this, that 2.25 capital T t0 upon r square s, and that becomes our equal to 1. So, in this way we get a new equation which is equation number 6 in this presentation, is s equal to 2.25 capital T t0 upon r square. Now, the value of t that is transmissibility can be obtained by this graph, noting that t oblique t0 equal to 10, then log t upon t0 equal to 1. And when we replace s by delta s, which is shown here, delta s, the change in the storativity, where the delta s is the drawdown difference per log cycle of t. So, in this way we also get that information as well. Now, earlier we have discussed this equation, that is equation number 5, and this equation then further becomes, after the understanding in the previous slide, this equation can be rewritten, and that becomes our 7th equation, that transmissibility equal to 2.30 q upon 4 pi delta s. So, now we are replacing delta s in that equation, and thus this procedure is the first to solve transmissibility with equation 7. As you can see, the output here is transmissibility, and then to solve s with the equation 6. So, 6 we have also dealt where we are solving the s. So, this method, and that is a Cooper-Jacob method, applicable only for small values of u, which we have discussed initially in this discussion, small value of u, and that means the u should be less than 0.01 to avoid any kind of large errors. This is important here, that only the condition here is that these values of u should be very small. Now, we have been doing pumping test mostly. So, we will be drawing the water. In previous discussions, I have also mentioned that recovery tests are also done, that how the drawdown is getting reduced or achieving the original level in the well, that is the water level in the well, and that will also give us values which should match with our pumping test values. Though recovery test may take long time to value to note down and then try to understand the entire scenario. So, here as we know that after once the pumping test is over, pumping we have stopped, and then water level in the pump and the observation wells will begin to rise, will begin to achieve the original level of water before the pumping. So, here what we are having on the right side a figure which is quite nicely demonstrating this recovery test, that this is the first section of in the x axis is the pumping period, and then suddenly once the pumping stops, then we are having now the recovery period, which you can see here. So, second part of the x axis is recovery period, and what would happen in the recovery period, there will be change in the water level with the time and after pumping, as this is the where the pumping has stopped. Now, the time which is lapsing or going on, we will put as a t dash, and this is the time small t in this. When pumping is being done, this is the drawdown, because this is the water level which you are measuring on the y axis. So, this becomes our drawdown, and when we plot this water level versus time, then this should be a curved line, and then when pumping stops, then it becomes the residual drawdown. That means the recovery will start, and this will be just opposite of what the drawdown in during the pumping period. So, this way we can also get a lot of information about our hydraulic characteristics of aquifer. So, the recovery of groundwater levels, while measurements of drawdown below the original static level, that is the prior to pump or original level, initial levels during the recovery period, are known as residual drawdowns. So, there will be a original level, pumping stops, now residual drawdowns. So, this you can also observe here, that the originally the water level was here, and then now it is left with this much gap. So, that is what we are saying here as residual drawdown, as mentioned also here. So, it is always good to measure residual drawdowns, not only the pumping drawdowns, but residual drawdowns, though we are calling as drawdown, but it should it is not really a drawdown, but it is a recovery curve or recovery cone. So, this residual drawdown becomes, because of all this, it is always good to measure, because residual drawdown, because analysis of data enables transmissibility to be calculated. In the pumping also we calculate the transmissibility, but during the recovery drawdown we can also recovery test. It is more appropriate word is during recovery test we can also get the transmissibility calculation or estimation. So, this provides an independent check on pumping test results, because whatever the values of transmissibility which were estimated, calculated during the pumping test can be verified, can be validated using the recovery test based transmissibility data. So, the cost of recovery test is not much, because it is a natural once the pumping has stopped, so this is there, and therefore, it is always advised that once the pumping has stopped, the readings in the water levels and time should continue, so that we can develop this kind of figure which is shown on the right side. Further, the rate of Q to the well during recovery is assumed constant and equal to the mean pumping rate. This is the assumption which we carry during the recovery test, and whereas pumping rates often vary when we are withdrawing water. In the first part of this figure, where we are withdrawing the water, the pumping rates can vary and are sometimes difficult to control accurately in the field. So, for that purpose also it is good that recovery tests should also be performed. So, if a well is pumped for a known period of time and then stopped, and then drawdown will shut down, the drawdown will stop further, and the drawdown after will be identical in that nature, that if we change it, only thing is that it is in opposite direction, but it would be identical in that sense, at least in theory, but it does not happen all the time. Anyway, there will be some residual gap, or some gap would be there, which will be ultimately recovered if we give more time to the aquifer to reach to the original water level. So, if the discharge had been continued, that means pumping has been continued, a hypothetical recharge well with the same flow are superposed on the discharging well, and at the instance the discharge is shut down. So, this can also happen. Now, we can come back to our famous Theis equation, and for the residual drawdown, and now we will call these values as dash. S dash can be given as that S dash equal to Q upon 4 pi T, and bracket W U minus W U dash, and this becomes our equation 8. Now, where we know that U equal to R square S upon 4 pi T. So, we can also write the same way for recovery test, U dash R square S upon 4 pi T dash. So, these are the same equations, except that we are now putting dash because of recovery test. So, just to distinguish between the pumping test and recovery test. So, the T and T dash are defined in the earlier figure which we have seen here. So, for a small r small and T large, T dash large, because the recovery time is large, we will give because it is not as like pumping. So, the well functions can be approximated by first two terms, it should have been 2 here, 2 terms of equations, 3 which we have earlier discussed, and which is S equal to Q upon 4 pi T bracket minus 5772 minus log E U plus U minus U square upon 2 L 2, and then U3, and likewise we keep writing depending on our requirements. So, therefore, the equation can be reduced, the above equation can be reduced to S dash equal to 2.3. Earlier also we reduced similar way, but there dash was not there, but now here for recovery test the same thing. So, for recovery test 2.3 q 4 pi t log t upon t dash. So, now again a plot of residual drawdown S versus S dash versus log t upon t dash forms a straight line as discussed in the earlier examples also. So, whenever you get the value, you can get the that straight line. So, the slope of line would be equal to 2.3 divided by 4 mu t for the delta S, and the residual drawdown per log cycle of the transmissibility becomes that t equal to 2.3 q upon 4 pi delta S dash. So, this there is no comparison of values of S can be determined by this recovery method. Now, one of the examples of recovery test is given here, that a pumping it is assumed that the Q was having a uniform rate, and though earlier we said that it is very hard to get uniform Q or uniform pumping from a well, but let us assume that it is uniform. That is one of the assumptions, which was the 2500 cubic meter per day was shut down after 240 minutes, and thereafter the measurement of S dash means recovery test, S dash and T dash tabulated, which is shown here in the figure, and that T dash is here and also S dash is here, units are also given here in an observation well, and determine the transmissibility. Ultimate aim is to determine the transmissibility during recovery test and compare these transmissibility values with the transmissibility which was obtained during the pumping test. So, now solution to this is that the T upon T dash are computed, which are also shown here, T and T dash are computed, and then T and T dash versus S dash plot is prepared on semi-log paper. So, this is that example here is that we are having on x axis T and T dash, and on the y axis we are having residual drawdown, that is S dash, and it is shown again, it is a straight line which you can see here. So, if I want to find the value anywhere with this best fit line, then I get it, also I get the delta S value here. So, this is the solution for the recovery test method for solution of non-equilibrium equations. So, a straight line as you can see in the right figure is fitted through points of delta S, which is equal to 0.4 is determined, then now we can put in the equation. So, the equation which we are going to use as discussed earlier also, that is T equal to 2.3 q upon 4 pi delta S. So, that would become when we substitute these values accordingly, then we end up with this, that T would be 1140 square meter per day. So, likewise we can determine the T during the recovery test also using the same equations as we have been using during the pumping test. The only difference here, while writing these equations, we are using these values with the dash. So, that way now the value which we get here can be compared with the previous discussions, where the T value would be almost same as during the recovery test. And that is why it is recommended that once the pump for a pumping test, once the pumping is stopped, the noting down of water level with the time should continue for longer time, so that we can also calculate the value of transmissibility during the recovery test, and then this value can be compared, so that we can validate that during pumping test whatever the variations in the output, that is whatever the variations in Q were there, which were assumed as uniform constant, But here, because here no energy is required, nothing, no pumping is done, you left, once you stop the pumping, then you left the aquifer to recover and to reach to the original level. As also discussed that to reach to the original level might be difficult or sometimes impossible, because if it is say pre-monsoon situation, so where you may not reach to the top or the original level of water in the well. But anyway, that residual thing will remain there, or the gap between original drawdown curve and that would be there, but nonetheless we can determine the T value and then compare with the pumping test. So with this I end this discussion. Thank you very much.